There's a metal that doesn't rust, doesn't age, and doesn't disappear. It just waits. Waits in water, in air, and even in our homes. What if I told you this metal spent centuries helping humans extract gold, fill cavities, and measure temperature, but at the same time slowly drove them insane and killed entire cities? Mercury, liquid silver, looks almost magical, but hides one of chemistry's most dangerous secrets. It can't be destroyed, it can only be hidden. And if you watch this video to the end, you'll find out where humanity is hiding mercury forever today, and why one mistake could bring it back into our lives. Mercury's story doesn't begin with shimmering droplets, but with a bright red mineral, cinnabar. For thousands of years, people used cinnabar as a pigment. Ancient Chinese and Romans made vermilion paint from it, decorating temples and statues. But cinnabar mining always came with tragedy. Workers in the mines suffered from mysterious tremors, delirium, and early death. The process of extracting pure mercury from cinnabar is pretty simple. The mineral is crushed and heated in special furnaces. At 675 degrees Fahrenheit, mercury vaporizes, then condenses as heavy silvery droplets. This ease of extraction made mercury accessible but also dangerously available. One of the most widespread uses of mercury in history was extracting gold and silver. Mercury has a unique ability. It instantly wets other metals, dissolving them and creating alloys called amalgams. During the gold rush era, prospectors mixed crushed ore with mercury. Mercury, like a magnet, pulled the tiniest gold particles from the rock, forming a thick paste. To get pure gold, they simply heated the amalgam over an open flame. The mercury evaporated straight into the air people were breathing, leaving pure gold at the bottom. This method, known as amalgamation, led to devastating contamination of rivers and soil across the globe. Even today, in the Amazon jungle, illegal gold miners use tons of mercury, poisoning ecosystems for decades to come. For a long time, mercury was considered irreplaceable in science and everyday life. In thermometers, mercury expands uniformly when heated, making it the perfect working fluid for precise temperature gauges. Mercury switches worked flawlessly for decades because liquid mercury conducts electricity beautifully and doesn't wear out. Amalgam fillings made from a mixture of silver and mercury were the standard in dentistry for over 100 years because of their incredible durability. But there was a dark side. In the 19th century, mercury was used to treat fur in the making of felt hats. Craftsmen constantly inhaled mercury vapors, which attacked their nervous systems. That's where the phrase "mad as a hatter" came from, immortalized by Lewis Carroll in Alice in Wonderland. The symptoms of poisoning, confusion, memory loss, and tremors became an occupational disease of entire industries. Mercury's real danger lies in its ability to bioaccumulate. When mercury enters water, bacteria transform it into methylmercury, an incredibly toxic organic form. It builds up in plankton, then in small fish, and finally, in large predators like tuna or sharks. A person eating that fish gets a massive dose of toxin. The most horrific example, the tragedy in the Japanese city of Minamata in the 1950s, where a chemical plant dumped mercury into the bay. Thousands died or were left disabled from brain damage. This event gave rise to Minamata disease and forced the world to consider banning the metal. Today, the Minamata Convention is in effect, signed by over 140 countries. It bans the production and export of mercury thermometers, pressure measurement devices, most types of fluorescent lamps, and the use of mercury in many industrial processes. If you break a mercury thermometer at home, it's a small-scale ecological disaster contained within a room. The mercury shatters into countless tiny beads that roll under baseboards and deep into carpet fibers. At around 70 degrees Fahrenheit, they start evaporating actively. One tiny mercury bead can poison the air in a closed space for months. Mercury vapor has no smell or taste, making it an invisible killer. Since mercury can't simply be burned or dissolved without a trace, it's a chemical element that doesn't break down. The only solution is complete removal and containment. It all starts at specialized facilities where millions of spent fluorescent bulbs, old medical devices, and industrial sensors end up. The first stage is mechanical shredding. For example, bulbs enter a sealed shredder that crushes the glass, aluminum bases, and mercury coating into fine debris. This mixture looks like trash, but it's extremely toxic, because every ton of this debris contains several pounds of mercury. By the way, mercury is incredibly heavy. A 1-liter bottle of mercury weighs more than 28 pounds. If you tried to lift a bucket of mercury, you'd be lifting 300 pounds. That's like 2 grown men. Next comes the main process, thermal desorption under vacuum. This mixture gets loaded into massive steel furnace reactors. The key feature here is the vacuum itself. When we pump out the air, mercury's boiling point drops. The furnaces heat the mixture to temperatures between 570 and 750 degrees Fahrenheit. Under these conditions, mercury starts evaporating intensely, separating from the glass and metal scrap. The vacuum system pulls out these toxic vapors, giving them zero chance to leak out into the workshop air. Next, the mercury vapor enters the condensation system. These are long coils cooled to low temperatures. As soon as the hot vapor touches the cold walls, it transforms back into liquid metal. Silvery droplets trickle down into special collection tanks. What comes out at the end is pure recycled mercury. However, since the world is gradually phasing out its use, this metal no longer returns to factories. The final stage is permanent imprisonment. The liquid mercury is mixed with special reagents like sulfur to convert it into a solid and stable compound. Mercury sulfide, which doesn't evaporate and doesn't dissolve in water. This substance is sealed in thick-walled steel containers, which are then coated with an anti-corrosion layer on top. These containers are shipped to underground storage facilities located hundreds of feet deep in abandoned salt mines or granite formations. There, in complete dryness and monitored by sensors, mercury is stored for decades. It's the only way to guarantee that liquid silver never reaches groundwater and doesn't come back to us through fish or water. Disposal is expensive and complicated, but it's the price humanity pays for the safety of future generations. Stand at Ground Zero, New York City. One World Trade Center rises 1,776 feet. Deliberate height honoring Independence Year. This building contains promise. It will never fall again. That promise lives in 45,000 tons of structural steel and 200,000 cubic yards of concrete. But concrete alone crumbles under stress. What gives it strength are 300 million pounds of steel rebar, ribbed bars running through every column, every beam, every floor. Each bar began as scrap metal melted at 3,000 degrees, rolled into ribbed shape, cut to exact length, trucked from South Carolina mill to Manhattan, and positioned with surgical precision. How does junked car become foundation of America's safest building? Why does rebar require ribs instead of staying smooth? Stay with us. You'll witness electric arc furnace creating artificial lightning and discover rebar's critical secret. Those ribs aren't decoration, they're mechanical bond preventing concrete from tearing itself apart. Nucor Steel Berkeley in South Carolina produced most rebar for One World Trade Center. This facility processes 2 million tons of scrap steel annually, and enough to build 12 Empire State Buildings yearly. The scrapyard stretches quarter-mile. Mountains of crushed cars, demolished buildings, retired appliances, old rebar from previous demolitions. Giant electromagnets lift entire automobiles, dropping them into sorting lines separating steel grades. Every day, 600 trucks deliver scrap. Every day, 400 trucks leave carrying finished rebar. Walk the scrap processing area. Shredders pulverize cars in 8 seconds. Same time it takes to read this sentence. Hydraulic shears cut structural beams like scissors through paper. The noise is relentless. Metal tearing metal, magnets clanging, conveyor belts grinding. One supervisor explains, "We see America's past arriving daily. Cars people drove to work, buildings where they lived, bridges they crossed. We melt history and rebuild tomorrow." For World Trade Center project, this facility operated 24/7 for 3 years straight, producing 3,000 tons monthly, enough rebar to circle Manhattan Island 40 times. The electric arc furnace transforms scrap into liquid steel through controlled lightning. This vessel, 40 feet diameter and 30 feet deep, contains 3 graphite electrodes 2 feet thick descending from roof. When 90 megawatts flow power for 70,000 homes, arcs jump between electrodes and scrap, generating 5,800 degrees. The scrap melts in minutes. Watch through protective glass as metal liquefies, glowing white hot then orange as temperature stabilizes. 200 tons of scrap loads per batch. The electrodes pierce the pile, current flows and artificial lightning strikes continuously. The sound resembles continuous thunder. The heat radiates through observation room despite water-cooled walls. Oxygen lances inject pure oxygen at supersonic speeds, burning impurities. Carbon oxidizes to gas, sulfur evaporates. Phosphorus combines with lime-forming slag that floats atop molten steel. Temperature control is absolute. Too hot wastes energy, too cool leaves impurities. Computer systems adjust power and oxygen flow thousands of times per melt, maintaining exact chemistry required for construction-grade rebar. Tapping releases 200 tons of liquid steel into ladle, refractory-lined bucket mounted on railcar. The pour takes 8 minutes, continuous stream of glowing metal creating updrafts lifting dust into air. Workers monitor from shielded stations, faces illuminated by orange glow. The steel, now 3,050 degrees, travels to continuous caster where transformation into solid bar begins. The caster pours molten steel into water-cooled copper mold, oscillating rapidly. As steel contacts mold, outer shell solidifies while interior remains liquid. The strand, continuous ribbon of solid steel, emerges from bottom, bent gradually from vertical to horizontal through roller system. Torches cut the continuous strand into billets 20 feet long, each weighing 4 tons. These billets, still glowing red at 1,800 degrees, feed directly into rolling mill. The entire process from scrap to billet takes 90 minutes. For WTC project, Berkeley ran 3 melts daily, producing 18,000 tons monthly during peak construction. The rolling mill transforms square billets into ribbed rebar through precision violence. The billet enters roughing stand where rollers squeeze and elongate it, reducing thickness while increasing length. Each pass through successive roller stands further reduces diameter. The steel, maintained at 1,600 degrees, glows orange-red, extending like taffy under roller pressure. 22 passes transform 4-ton billet into 500 feet of rebar. But here's where rebar gets its identity, the ribs. Special roller dies emboss transverse ribs and longitudinal ridges onto surface. These aren't decorative. The ribs increase surface area by 40%, creating mechanical bond with concrete. Smooth bar would slip under stress. Concrete would crack and fail. Ribbed bar locks into concrete through friction and mechanical interlock. The rib pattern follows precise standards. Height, spacing, angle, all controlled to thousandths of inch. For WTC, specifications demanded grade 75 steel, yielding at 75,000 psi, 3 times stronger than standard residential rebar. After rolling, the rebar, still 800 degrees, enters cooling bed where water jets control cooling rate. Fast cooling creates hard but brittle steel. Slow cooling produces soft but weak steel. Controlled cooling achieves optimal balance. Computer systems adjust water flow based on bar diameter, steel grade, ambient temperature. The bars cool from orange to black in minutes, steam rising in clouds. Then comes straightening. The hot rolling process introduces slight curves. Straightening machines grab bars between sets of rollers positioned at angles, pulling and pushing until perfectly straight. Deviation under 0.01 inches per 40 feet. Next, shearing machines cut bars to exact length. For WTC, typical lengths were 40 and 60 feet. sized to fit concrete forms with minimal waste. Flying shears cut moving rebar at speeds exceeding 20 feet per second. The cut must be square, clean, burr-free. Each bar gets stamped with grade marking and mill identification. Quality control happens continuously. Samples from every heat, every batch of melted steel undergo testing. Tensile machines pull specimens until they break, measuring yield strength, ultimate strength, elongation. Chemical analysis verifies carbon, manganese, silicon content. Dimensional inspection confirms rib height, spacing, and bar diameter. Every bar carries traceability, heat number linking it to specific melt, specific chemistry, specific mechanical properties. For one World Trade Center project, quality standards exceeded normal construction. The Port Authority required additional certifications, independent testing, complete documentation. Rejected bars got remelted. No shortcuts existed. One quality inspector recalls, "Every bar we shipped could end up in critical structural element. We tested knowing thousands of lives would depend on our work being perfect." The facility maintained 99.8% acceptance rate, meaning just 2 bars per thousand required remelting. Rebar's invention dates to 1850s France, when Joseph Monnier, a gardener, reinforced concrete flower pots with iron mesh. He discovered concrete's compression strength, combined with iron's tensile strength, created superior material. By 1900s, rebar became standard in construction. The ribbed surface pattern emerged in 1930s after engineers realized smooth bars failed under dynamic loading. Earthquakes, wind, vibration caused concrete to slip along smooth bars. One World Trade Center's foundation began in 2006, final steel placed in 2012. During construction, 600 trucks daily delivered materials to Manhattan site. Rebar arrived on flatbed trucks, each carrying 25 tons, 40 to 50 bars per load. Cranes lifted bundles to specific floors where iron workers tied bars into 3-dimensional cages matching structural drawings. For the concrete core building's spine, rebar spacing was 4 inches on center in both directions, creating steel mesh so dense you could barely see through it. Environmental impact shows interesting paradox. Producing rebar from recycled scrap uses 60% less energy than making steel from iron ore. Berkeley facility prevented mining 200,000 tons of iron ore annually. Yet steelmaking remains carbon intensive. Melting metal requires massive electricity. Each ton of rebar generates 1.8 tons CO2 emissions. For WTC's 300 million pounds, that meant 270,000 tons CO2, equivalent to annual emissions from 30,000 cars. Here's the secret we promised. Rebar ribs create mechanical bond, but their real genius is crack control. Concrete always cracks. Thermal expansion, settling, loading all cause microscopic fractures. Smooth rebar allows cracks to propagate, widening until failure. Ribbed rebar intercepts cracks, distributing stress across multiple ribs, preventing single crack from becoming catastrophic failure. Those ribs transform concrete from brittle material into ductile system that bends before breaking. At WTC, this matters profoundly. The building must survive impacts, explosions, earthquakes that would destroy conventional structures. From South Carolina scrapyard to Freedom Tower rising above Manhattan, the transformation completes. Nucor Berkeley melted America's discarded metal and reformed it into symbol of resilience. That rebar, 300 million pounds of it, creates skeletons stronger than original towers. Every bar positioned perfectly, every connection inspected, every pore documented. The building stands because thousands of workers understood. This isn't just construction, it's promise. Promise that engineering will triumph over terror, that steel and concrete and human determination can create something genuinely unbreakable. Those ribs running through every column aren't just preventing concrete failure, they're preventing failure of a different kind. The failure to rebuild, to remember, to rise again.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena, lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious. Invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust. Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore, they process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries. Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers, rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal. Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained, recycled endlessly.
Carbon emissions dropped 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
Inside a steel mill, molten iron glows white at 3,000 degrees. Workers stand 50 feet away. The radiant heat still blisters exposed skin. But look closer at what contains this liquid fire. Gray bricks line the furnace walls, glowing dull orange, yet holding firm. These aren't ordinary bricks. Touch regular clay brick to molten metal and watch it explode into steam and fragments. So what material survives temperatures hotter than volcanic lava? What invisible shield protects every furnace melting metal, making glass, or firing ceramics worldwide? Stay with us. You're about to discover why engineers kill clay to make it stronger, and the counterintuitive secret of double firing that transforms fragile earth into industrial armor, surviving conditions that vaporize steel.
Our story begins in Missouri clay. Deposits formed 60 million years ago when ancient seas deposited aluminum-rich sediments. Excavators rip into hillsides, extracting clay containing over 40% alumina, the magic ingredient. Regular pottery clay melts around 2,000 degrees. High alumina clay? It laughs at 3,000. Watch the extraction crew. They're not just digging dirt, they're harvesting geology's accident. This specific clay formed under precise conditions. Volcanic ash settling through prehistoric oceans, compressed over epochs. The foreman walks the pit daily, examining color and texture. Too much iron content? The clay turns red and weakens. Perfect batches shimmer gray-white, almost ghostly. Every ton supports industries most people never see, but everyone depends on.
The clay arrives at processing facilities caked with impurities. Massive crushers reduce house-sized boulders to gravel. Water floods the mixture, creating liquid slurry pumped through magnetic separators. Powerful magnets extract iron particles. Even microscopic contamination causes problems later when heat turns iron into weak spots. Picture the filtration building. Workers monitor screens showing particle sizes measured in microns. The slurry flows through increasingly fine meshes, removing everything except pure clay molecules. The process mirrors diamond cutting, patient, meticulous, unforgiving. One foreman's been doing this 30 years. Clay's honest, he says. Screw up purification, the furnace tells you months later when bricks fail. By then, you've shut down a steel mill.
Here's where it gets strange. Before making bricks, they destroy the clay. Giant kilns, tunnel ovens stretching 300 feet, fire raw clay at 2,400 degrees. The material transforms. Water molecules trapped in crystal structure evaporate. Crystals fuse together. The clay dies, becoming chamote, fired aggregate resembling brown gravel. Watch workers dump glowing chamote onto cooling floors. Steam erupts as residual moisture hits air. The material has lost its plasticity forever. You can't reshape it. You can't mold it. Ancient potters would call this ruined clay. Modern engineers call it the secret ingredient. This dead material becomes the skeleton that prevents shrinkage when the final brick gets fired. It's already survived hell once, it won't flinch the second time.
Now the resurrection begins. Crushers pulverize shamat into particles ranging from sand size to powder. Meanwhile, fresh raw clay gets mixed with water, creating a binding paste. The ratio matters obsessively. 70% dead shamat, 30% living clay. Too much shamat, the brick crumbles. Too little, it shrinks catastrophically during final firing. Imagine construction workers mixing concrete, but every batch costs thousands, and failure means industrial catastrophe. The mixing drums rotate for 40 minutes. Technicians pull samples constantly, checking consistency. The mixture emerges as damp, grainy paste. Looks like chunky peanut butter, but feels like dense sand. This strange hybrid contains both the dead and the living, the fired and the raw, the stable and the flexible.
Hydraulic presses generate forces exceeding 2,000 tons, compressing the clay shamat mixture into brick shapes. The pressure is critical. It determines density, which determines strength. Watch the press operator. He's worked this machine 18 years. His hands hover over emergency stops, eyes tracking pressure gauges. The bricks emerge slightly damp, surprisingly fragile. You could break one with a hammer. Workers stack them on kiln cars, steel platforms holding thousands of bricks. The cars roll into drying chambers where warm air removes moisture over 72 hours. Dry too fast, surface cracks. Too slow, production bottlenecks. The drying supervisor walks the chambers constantly, adjusting airflow by feel and decades of experience.
The final firing begins. Kiln cars enter tunnel kilns heated to 2,600 degrees. The journey takes 48 hours, crawling through zones of increasing temperature. In the first zone, remaining moisture evaporates. Second zone, raw clay begins sintering, particles fusing at edges. The critical third zone pushes temperatures beyond anything the bricks will face in service. You can't see inside operating kilns. The heat would blind you instantly. But infrared cameras reveal the transformation. The bricks glow yellow, then white. At peak temperature, individual clay particles fuse into dense ceramic matrix. The shamote, already fired once, provides dimensional stability, preventing the shrinkage that would crack ordinary clay. When bricks finally exit, they've transformed into material that will outlast the furnaces they protect.
Quality control seems simple. Drop the brick. It should ring like a bell. Clear, sustained tone indicates proper firing and density. Dull thuds mean hidden cracks or insufficient firing. Experienced inspectors can diagnose problems from sound alone. "That's a Saturday brick," one inspector says, tapping a dull specimen. "Someone rushed the firing before weekend. Rejected." But sound testing is just the start. Samples get crushed in hydraulic presses, measuring compressive strength exceeding 10,000 psi. Others get thermal shocked, heated to 2,000 degrees, then water quenched. Survivors prove they'll handle the brutal thermal cycling of industrial furnaces. Failure rate must stay below 0.5%. Even one weak brick can collapse a furnace wall, causing million-dollar shutdowns.
Refractory technology emerged from ancient pottery kilns. Early Chinese potters discovered high alumina clay fired harder than anything else. By 1300 AD, Chinese furnaces using primitive refractories reached temperatures melting iron, a feat Europeans wouldn't match for 4 centuries. The Industrial Revolution demanded better. In 1879, Sidney Gilchrist Thomas invented basic refractory lining, enabling the Bessemer process to use phosphorus-rich iron ore. Suddenly, Britain's massive ore deposits became viable. The discovery shifted global power. Whoever controlled refractory technology controlled steel production. Today, specialized refractories enable everything from semiconductor manufacturing to rocket engines. The global industry moves 50 million tons annually. Invisible infrastructure supporting visible civilization.
Carbon emissions dropped 41% using modern refractories versus 1950s technology. Better insulation means less fuel heating furnaces. Industry saves $78 billion annually through extended furnace life. Modern refractories last 5 years versus 6 months for old materials, slashing replacement costs. Here's the secret we promised. Refractory bricks work because they're already dead. That double firing process, burning the clay into cement, then mixing it with fresh clay and firing again, creates material that's experienced worse than anything it'll face. The cement has no shrinkage left to give. The fresh clay binds it together, then dyes itself during final firing, becoming equally stable. From ancient clay to modern armor, the cycle completes. We've learned that sometimes strength requires destruction first. Kill the material, resurrect it, kill it again. Only then does it become immortal, standing guard in furnaces that never sleep, protecting the industrial processes keeping civilization running. That humble gray brick isn't just holding back heat, it's holding back chaos.
The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the 4th largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor.
At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel, but there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousands of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this: more than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.